In these next few videos, I want to look at a high-level review of everything we've done in Unit 2. So that's from week 4 until today. So just like with last time with Unit 1, these review videos should not be a substitute for going back through the original material, but I just want to highlight some of the high-level concepts we've picked up on. So this unit has been all about mechanical loading, which is as follows. What if you take a piece of biological tissue, maybe a bone or a tendon, a ligament, and you apply a force to it? What happens? That's the key idea of mechanical loading. And in this unit, we started out from a very simple idea of taking a piece of tissue, like maybe the Achilles tendon, and plotting its deformation maybe you measure that in millimeters, as a function of the applied force. And we saw that there's some characteristic shape to that. Then we took the next step and said, well, what if we control for the fact that different tissues in the body, different tendons, say, have different cross-sectional areas and different lengths. So that led us to one of the key ideas of this unit, which is the stress-strain curve. So moving from force, we said, well, let's plot stress as the force divided by the cross-sectional area. Sometimes we use this sigma to mean stress, but let me write it out. And then likewise, for deformation, we said, well, what if we just expressed deformation, meaning how stretched out a tendon or a bone or a ligament or cartilage is, just as a percentage change from its original length. So percentage of change in length, which we usually just write that as strain. So this gave rise to this idea of stress-strain curves. So maybe you take a tendon and you see how it deforms, meaning what its strain is, as a function of how much stress, meaning force divided by cross-sectional area, you apply to it. And maybe you get something like this, and then it breaks up here. We saw that these stress-strain curves have a few characteristic components to them. First was this region on the left here called the toe region, which is not something you see in every material, but is something you see in tendons, in ligaments, and in cartilage. And we saw that there's this linear region in here where the material is behaving more or less like an idealized spring. And we can connect the slope of this stress-strain curve right in this region with the stiffness of the material, but normalized to its to per unit cross-sectional area. On our original force deformation plot up here, the slope was really literally the stiffness, as in like the physics class spring stiffness. Down here is the same idea, but it's just something called either the Young's modulus or the modulus of elasticity. But the idea is the same, in that the steeper the slope, the stiffer the material, meaning the stiffer the spring-like behavior. Then we saw up here, we had this plastic region where the material is starting to get damaged and it's deforming. And there's a special point right here called the ultimate strength, where that's the maximum amount of stress that the material can handle. And then down here we have yielding, and then the material just breaks. Right? The tendon snaps, the ligament snaps, the cartilage ruptures, and so on. We also saw there was a few more advanced concepts we can think about with the stress-strain curve. So suppose we don't go up all the way until this breaks, and I'm just using shorthand here, sigma for stress and this epsilon for strain. Suppose we don't go all the way up until the, say, tendon or ligament breaks. Suppose we just go up like this and then come back down. So we stretch it out and then we unstretch it. We release it. So first off, when we go up like this, one way we can think about the behavior of the stress strain curve is that the area under this curve is the amount of energy stored in the spring, in the material. And then when we go back down, we get to release that energy. Now, you may remember there's a caveat, and that caveat is when we go back down, we don't get 100% of the energy back because the stress strain curve on the way down, so this is like going up, was like this. But when we go down, we go like this. This behavior has a name. It's called hysteresis. And that refers to the fact that when we went up, we stored up this much energy. But when we went down, we only got back the area under this curve, which means that the area in the middle, meaning this amount of energy, is energy that's lost, usually to heat. So that's like an energy loss. And usually with like a tendon, maybe it's about 10%. 10% of the energy is lost. We also saw another more advanced property of some materials called viscoelasticity. And what that means is that suppose you load a tendon slowly. You load it on the way up, and then it comes down like this, exhibiting that hysteresis we just saw. But if you load a tendon really quickly, you get a little bit different behavior. You get something like this. The thing to notice here is that the slope is steeper, meaning this is like the high loading rate, meaning the rate at which you apply force, and this is the low loading rate. So this viscoelasticity, maybe write that out. Is a property that we see in tendons and in ligaments and in cartilage. And it's kind of useful because it allows us to have a effectively stiffer material in our body when the loading we encounter is greater. So it helps protect us from injury. And it also helps us store up more energy. Lastly, in week 4, we saw the different types of mechanical loading. So that's essentially if you're applying a force to, say, some object, what are the different ways in which you can apply that force? So maybe I have a little like slice of, I don't know, cartilage here. We saw that there is tension, that's like if you stretch something out. So tendons and ligaments experience a lot of tension, right? They're designed to handle tensile forces. You can also do the opposite. You can push on something. You can compress it. This is compression. So bones, for example, are highly adapted for handling compressive loading. We also saw there was this interesting combination of both of them, which is bending. So maybe I can sketch out how bending looks. So suppose you bent this. It might look like, and of course I'm exaggerating here, but it might look like this. And notice how that would induce compression on this side and tension on this side. So this part, if we bent kind of this way, this part would be getting pulled apart here, and then this side would be getting squished together. So you can think of bending as tension on one side, compression on the other side. Another type of loading we saw was torsion, which you can probably guess just based on the name what that is. That's like when you twist something. So imagine we took something like this and we applied a twist to it. So what would happen is maybe it would, let's see, twisting like that. And so these would kind of go around like that. Doing my best to draw this in an exaggerated way here again. And there was one more form of loading we saw, which is shear. And we saw how shear is like an offset version of compression. So shear, what I mean by that is, again, suppose we have this say it's a piece of cartilage. And cartilage is a good example, by the way, of tissue that experiences shear based on the forces it encounters in joint spaces. So suppose instead of compressing it kind of head on with forces like this would be compressing in this direction, right? Suppose instead we said, okay, one force like this, one force up here like this. That would have a tendency to cause shear, and that would look kind of like this. If this is like a block of jello, it would deform like that, right? Because this force is trying to push the bottom this way, and this force is trying to push the top the other way. So that's shear, and these are the 5 types of mechanical loading that are encountered inside the body. So broadly, that was the material that we encountered in week 4, and if any of these topics are a little hazy for you, I would recommend you go back and watch the specific videos on each of these topics from that week, or look over the lecture notes that I have uploaded as a PDF on Canvas.